If you were listening to this deep dive right now,
Yeah.
uh, there's a pretty good chance it's late.
Probably very late.
Right. You've got your IDE open, maybe on one monitor, and the glow of your terminal is just kind of reflecting off your coffee mug.
The classic late night coding session.
Exactly. And you're sitting there trying to figure out the exact architecture for like the next great AI application.
And if that is you, you know exactly how magical it feels the very first time you interact with a large language model.
Oh, it's incredible. You shoot off a prompt, it responds, you ask this highly specific follow-up question, and it gets it.
Yeah, it feels like this continuous, living, breathing conversation.
But here is the wild part, the thing we're going to completely tear apart tonight. That continuous intelligence, it is entirely an illusion.
A very convincing illusion, but yeah, it's fake.
Right. When you talk to an LLM, you feel like you're having this flowing, stateful dialogue. But the core inference engine, the actual model, remembers absolutely nothing.
Nothing at all. The model itself is, it's entirely stateless.
Which is crazy to think about, given how smart it seems.
Well, we get so caught up in the sophisticated reasoning of the output, you know? We just completely overlook the reality of the underlying infrastructure. It is inherently amnesiac.
Okay, let's unpack this. Because for anyone building these tools, for the engineers listening right now, this is the ground floor.
Yeah, you have to understand this before you can build anything real.
Exactly. So today's mission is a deep dive into the architectural realities of building an LLM-based chat application.
We're looking at the specific mechanisms, right? From active memory management to front-end latency masking.
And right down to multi-tenant security. Basically all the back-end plumbing required to manufacture that seamless conversational illusion.
And what's fascinating here is how this fundamental limitation, this amnesia, it completely shifts the burden of work.
It shifts it away from the data scientists building the models, right?
Exactly. It lands directly onto the shoulders of the application developers.
So like when users interact with a modern chat interface, they assume the AI is holding their context in some kind of, I don't know, active neural memory bank.
Right. They think the AI is remembering them. But structurally, there's no thread on the model's end.
So to maintain state, the application layer has to do all the heavy lifting.
It does. It has to capture the incoming user message, query a database for the historical context, bundle it all up into the single massive string array.
And then send that entire package over the API for every single turn of the conversation.
Yeah.
Every single time you hit enter.
Every single time.
I always think of it like interacting with an incredibly brilliant savant who has a severe instantaneous case of short-term memory loss.
That's actually a perfect analogy.
Right. Because you walk into a room, you introduce yourself, you outline this really complex coding problem, and they give you a brilliant solution.
But if you walk out
Right.
and then walk back in 30 seconds later,
They have zero idea who you are.
no.
So to ask a follow-up about that code they just wrote, you literally have to hand them a physical transcript of everything you just discussed.
You'd have to say, okay, read this transcript from top to bottom. Good. Okay, now based on that, here's my next question. And that's exactly what the API payload is doing. The intelligence, the reasoning capability that absolutely lives in the neural network weights.
But the responsibility for making it a persistent conversation.
That lies squarely on your back-end application logic. The state management, the continuity, that's on you as the developer.
Because if your database read is slow or, I don't know, your context array drops a critical object.
The illusion shatters immediately. The model will just confidently hallucinate because it can only reason based on the exact array of messages you just handed it.
Right. Garbage in, garbage out. Which brings up the core architectural bottleneck here.
A context window.
Yes, because we have to send this massive transcript over the wire every single time we hit a hard limit. The context window is the absolute upper limit on the number of tokens the model can process in one go.
And it shapes every single architectural decision you make.
So looking at our sources, it seems like developers generally rely on 3 specific patterns to manage this growing payload.
Yeah, 3 main strategies.
The first one is just the full history approach.
Yeah.
You literally just append every single prompt and response to the array and fire it off.
And for very brief interactions, I mean, it's the most straightforward implementation.
Like a simple triage bot.
Exactly. If you're building a customer service bot that only ever handles 3 or 4 back and forths before routing to a human, you get absolute fidelity.
The model sees exactly what was said in the exact order it was said.
Right. No compression, no loss of context.
But hold on, let me push back on this a little bit. Because compute gets cheaper every single day,
Yeah.
generally speaking.
And we're seeing models now with context windows of 128K, even a million tokens. So why is this actually a bottleneck?
Why?
Like, why not just use full history for everything and dump the whole 20-page transcript into the payload? Who cares if the array gets massive? If we connect this to the bigger picture, it's because compute isn't getting cheaper linearly when it comes to transformer architectures.
Ah, right. The math doesn't scale nicely.
Exactly. The attention mechanism inside the model, which is the part that actually analyzes the relationships between all those tokens, it scales quadratically.
So it's an O of n squared complexity problem.
Right. So as your array grows, your API costs do not just tick up gently, they explode.
Ouch. So a long conversation could cost you a fortune.
Oh, absolutely. But even if you have unlimited money and you don't care about the financial costs, your latency degrades exponentially.
Meaning the app just gets slower and slower.
Way slower. Your time to first token, or TTFT, becomes agonizing. You might have a million token window, but if you actually use it, your user is going to be staring at a spinner for 30 seconds waiting for a reply.
Oh, wow. Yeah, the latency hit alone would completely kill the user experience. Nobody waits 30 seconds for a chat response.
Nobody.
Okay, so if full history is a scale killer, that brings us to the second pattern, the sliding window.
Right, which is basically a truncation strategy.
So instead of sending everything, we just cap the array. Say, we only send the last 10 messages. Once message 11 comes in, we just drop message 1 entirely.
It acts as a strict bounding box on both your financial costs and your latency.
So it's predictable.
Very predictable.
Yeah.
By capping the array length, you guarantee that your token count will never exceed a specific threshold.
But the UX tax on that is brutal, isn't it?
It really can be.
Like, imagine I'm a user, and my very first message was a highly specific instruction, like, write this script in Python, do not use any external libraries, and make sure it handles asynchronous calls.
A classic developer prompt.
Right. And then we go back and forth debugging a specific function for 20 minutes.
And eventually that first instruction slides out of the window.
Exactly. The moment that first instruction drops out of the 10-message limit, the model is going to completely rewrite the whole script in JavaScript using 3 different NPM packages.
Yep. Because the model didn't forget, your application layer actively hid the constraint from it.
That would be so frustrating as a user.
It is. It's a blunt thresholding tool. I mean, it solves the back-end engineering problem of unbounded latency, but it actively degrades the user's perception of the AI's intelligence.
Which is exactly why production-grade applications almost universally rely on the third pattern.
Summarized history.
Right. Instead of blindly dropping the past, you actively compress it.
It's the most elegant solution, but also the most complex to build.
So what does this actually look like in the back end? Because we aren't just running a simple regex script to shorten words.
No. You're actually utilizing asynchronous background workers to run a secondary AI model.
Usually a smaller, faster one.
Exactly. And its only job is to compress state.
So as the user interacts with the system, you maintain a short buffer of the raw, most recent messages, like a microsliding window.
Right, just the last few verbatim messages. But simultaneously, an async worker, maybe a Celery task or a Goroutine, takes the older messages and passes them to that cheaper model.
And what are we asking that secondary model to do?
You prompt it to extract facts, user preferences, and core constraints. It generates a dense semantic summary of the conversation so far.
Man, that sounds like a massive synchronization headache.
Oh, it's a nightmare if you don't orchestrate it perfectly.
Because my payload going to the main model becomes this weird hybrid structure. I've got a system prompt, followed by a dynamically generated dense summary of the first 20 minutes of the chat.
Followed by the verbatim text of the last 3 recent messages.
And then followed by the user's brand new input.
Exactly. And managing that hybrid structure is where the real engineering happens. You have to ensure that the background summarization finishes before the user sends their next message.
Or you have to handle the race condition of a pending summary state. Like, what if they type too fast?
Right. But when executed correctly, the context window retains a highly compressed note. Something like, user requires Python, no external libraries, asynchronous execution.
So the main model keeps the critical constraints, your token payload drops by like 80%, and your time to first token stays razor sharp.
Exactly. It's the best of both worlds.
Wait, though. If we are doing all this orchestration database reads, checking token thresholds, occasionally waiting on a background summarization task before we even ping the main API, the latency still has to stack up.
It does. There's an unavoidable delay.
And we just said that a user staring at a blank screen for even 5 seconds is a death sentence for a web app. It feels exactly like a frozen loading bar.
They start wondering, did my Wi-Fi drop? Did the server crash?
Right. So how do we fix that?
This is where back-end architectural constraints force front-end innovation. To mask this unavoidable delay, you implement streaming.
Okay, getting the words on the screen one by one like it's typing.
Exactly.
But structurally, how are we piping that to the client? Are most engineers spinning up WebSockets to handle this bidirectional chat?
You'd think so, but actually, WebSockets are often overkill for this specific mechanism.
Oh, really? Why is that?
Because the communication during the text generation phase is strictly unidirectional. It's just the server pushing tokens down to the client.
Ah, okay. So what's the alternative?
The industry standard is server-sent events, or SSE.
Right.
It's much easier to scale through load balancers, it works natively over standard HTTP, and it perfectly matches the stream of tokens coming out of the LLM API.
And the psychological impact of SSE is just massive. When you see the words appearing one by one, your brain interprets it as the AI thinking and typing in real time.
It totally changes the perception of speed. Even if the total time to generate the entire paragraph is exactly the same as a single blocked request, the perceived latency drops to nearly zero.
Because you are engaged, the millisecond that first token hits the
Yeah,
UI.
exactly. It functions as a psychological bandage for a back-end bottleneck. The user is distracted by the text generation, buying the system the time it needs.
That's brilliant. But front-end features in AI apps go beyond just masking latency, right?
Oh, for sure. Think about the stop generating button.
Right, the little square stop icon.
In a traditional CRED application, a stop button is just a convenient UI cancellation. But in an LLM application, it is a critical context window management tool.
Oh, I see where you're going. Because if the model goes off on a complete tangent, you're not just wasting time. You are actively polluting your own database.
Precisely. If the model starts writing 3 paragraphs of useless code and you don't stop it, your application is going to append that garbage to the conversation history.
And then on the next turn, that garbage is going back into the context window.
Confusing the model even further, you are paying the API to generate bad data and then paying again to submit that bad data back as context.
So when a user hits the stop button, the abort controller, the front end cuts the stream, but critically, it must also signal the back end.
Yes, it has to tell the backend to truncate the database entry at that exact token. It prevents a bad data feedback loop.
Wow. So what does this all mean for the UI UX developer? It means the interface isn't just a glossy layer of paint over an API.
Not at all. The front-end components, the stop buttons, the ability to edit a previous message, they are structural control panels for active memory management.
So by letting a user edit a previous prompt, you are effectively letting them rewrite the history transcript before you send it back to the amnesiac model.
The interface and the state management are inextricably linked.
That's fascinating.
And discussing state management and database appending leads us to really the most critical, high-stakes aspect of this entire architecture.
Security.
Exactly, because when you are building this application, you are not just managing one user's transcript, you are dealing with thousands of concurrent requests.
Dynamically assembling context arrays from a database and firing them off to a third-party API.
Right, which brings us to the absolute non-negotiable imperative: session security and isolation.
Because let's look at the reality of what people are actually pasting into these chat boxes. It's not just like pancake recipe.
Fair and close.
It's proprietary back-end code, highly sensitive financial forecasting, personal health symptoms. People tell these bots everything.
They really do. And in a multi-tenant environment, if your state management leaks context from one session into another, it is a catastrophic security failure.
Because the LLM has no concept of permissions.
Right.
Or data classification.
Zero. It just evaluates whatever array it is handed.
Okay, let's walk through a nightmare scenario here. Let's say I'm building my app, and I'm using an in-memory cache like Redis to store these recent message buffers, just to keep the latency down.
A very common approach.
Right. But let's say my caching logic uses the improperly scoped session ID. Or there's an unhandled promise rejection that mutates a shared state variable under heavy load.
Okay, I see where this is going.
Is it actually possible that my server accidentally grabs the highly sensitive summarized history of user A, who is asking about a confidential corporate merger, and appends it to the API payload of user B?
It is entirely possible. In fact, it has happened in poorly architected systems.
Wait, really?
Yes. If thread B's session ID points to a corrupted cache key, your server will happily stitch user A's confidential merger details right into user B's context array.
Oh man, so user B asks for a pancake recipe.
And the model seamlessly hallucinates a response that integrates the pancake recipe with the details of the corporate buyout.
Because again, the model trusts the application layer completely. It assumes everything in the array belongs to the current user.
That's the scary part. The model becomes a laundering mechanism for leaked data.
User B might not even realize they are looking at someone else's real confidential information because the LLM presents it so smoothly and confidently.
Exactly. This is why strict data siloing is the highest stakes component of the build. Every single database query must be rigidly scoped to the authenticated user ID.
Not just a transient session token, right?
Right. And your connection pools must be flawlessly isolated. You are essentially building a highly sensitive data pipeline where every single incoming request is a potential vector for cross-contamination.
If the engineering wrapper isn't airtight, the whole thing falls apart.
It really puts a massive responsibility on the engineer.
You definitely can't just slap an API key into a front-end framework and call it a day.
No, you really can't.
So just to pull all of these architectural threads together, we started by recognizing the fundamental statelessness of the LLM inference engine, the amnesia.
Right, the core limitation.
And from there, we explore the trade-offs of our memory patterns, realizing that full history scales quadratically, sliding windows punish the user experience, and background summarization requires all that complex asynchronous orchestration.
Which is a heavy lift, but necessary.
Then we looked at how SSE streaming and UI controls mask the back-end latency and actually help prune context window pollution.
It's a psychological bandages.
Exactly. And finally, we highlighted the critical necessity of multi-tenant data isolation to prevent those catastrophic context leaks.
It is a phenomenal amount of invisible work.
So much work that the user never sees.
But when the asynchronous queues, the cache layers, and the streaming connections all execute in perfect harmony, the technological constraints completely fade into the background.
And the user simply experiences a machine that appears to understand them.
That's the goal. That's the illusion we're all chasing.
It really is.
Yeah.
But our exploration into building these systems doesn't end with state management. Tomorrow, this deep dive shifts gears entirely.
Oh, tomorrow's going to be great. We are moving from how we handle memory to how we handle meaning.
Right. We're going to explore the architecture of semantic search and vector databases.
We'll look at how you take raw text, convert it into mathematical embeddings, and build a system that can query a massive data set.
Based on what a user means, not just the keywords they type.
Because vector databases introduce an entirely different set of scaling and latency challenges, especially when you try to integrate them back into the LLM context window we just discussed today.
It's going to be an essential follow-up for sure.
Definitely.
Well, until then, as you turn back to your terminal and stare at those chat interfaces you're building or integrating, consider this final thought.
Think about that magical, continuous conversation you just had with an AI.
Consider how much of that magic isn't actually the neural network at all. The real magic is the meticulous, heavy-lifting software engineering wrapper that developers just like you have designed.
Perfectly calibrated to hide the machine's raw, amnesiac limitations.
Keep coding, build secure systems, and we'll see you on the next deep dive.